Today, it is my immense pleasure to introduce Peter Corke. Peter is a distinguished professor of robotic vision in Queensland University of Technology in Australia. He is also the director of the Centre for Robotics and the director of the QUT Centre for Excellence for Robotic Vision. Peter's research is all about enabling robots to see the world. And if you're working on robotics, chances are that the work of Peter has influenced you at some point. He is the one behind the invention of the robotics and machine vision toolboxes for MATLAB and the founder of Robot Academy. All these incredible resources are free and open to everyone. He has made so many contributions to the field of robotics, and we are very happy to have him here today in this last session before the summer break. Peter will talk about the history of robotics, the challenges we face, and where we should focus on the future. The idea is to have Peter making the presentation, and then we will engage in a moderated Q&A. Peter, thank you so much for being here today, and I will give you space to share your slides now. You're muted.
I was muted. Patricia and Sylvia, thank you so much for the introduction and the opportunity to be here today. Is that shared, or are you seeing my whole desktop again?
We see everything.
Why does this keep happening to me? There we go. Okay, so this is going to be a not technical talk. It's going to be a bit of a retrospective look at the field of robotics. I'm going to touch on some challenges, frustrations that I have. I really worry that as a field, we're not progressing nearly as quickly as we should. And as one gets older, the rate of progress becomes important. I want some of these things to be sorted out and working before I retire or expire. So I'm going to talk about some of those issues today. Hopefully can start an argument or a conversation, and we can chat about that at the end. All right, I'm going to start by going backwards into the past. So I was at primary school in 1963. And everything was about the space program. I was a geeky kid even at that age, and I guess I wanted to be an astronaut. Probably most kids did at that particular point in time. And okay, if I couldn't be an astronaut, then maybe I'd be one of these guys in a white shirt and tie in mission control, or an engineer designing rockets or satellites. So from a very young age, I knew that I wanted to do something technical. And it was absolutely an optimistic time when it came to technology. And so some books and things that I had as a kid, and some of these things are from scrapbooks that I made when I was a kid. There was talk about robots and computers and machines and space travel. It was enormously optimistic. So as a child of the early 1960s, sort of you grow up with particular expectations about the way the future is going to unwind. And I have to say, it hasn't unwound in the way that we were led to believe back in this highly optimistic time in the 60s. So there would be space stations, huge, big space stations shaped like wheels with lots of rooms and all sorts of facilities on board. And this is a concept drawing from 1952, this is from way before I was born even. So there would be amazing space stations and there would be amazing robots. So all the TV programs from the 1960s, many of them had robot characters, and they were very capable, ironic, witty, clever, all of those things. So that was quite some expectation about technology. And as a technologist, I guess I figured that I would be part of that revolution. You know, I'd be helping to create these amazing technologies. But the way things panned out, I'd have to say, is a bit of a disappointment. So, you know, instead of the great space station envisaged by Wernher von Braun, We have the ISS, which is tiny, and inside is just a complete schmozzle. It's cramped, it's small, it's untidy, and all of that. And instead of those elegant robots that we saw on TV, we got ROS, right? So from what I expected as a child to what we actually have, it's somewhat disappointing. So I want to talk a little bit about the dissonance between perhaps the dream, the vision, where we are now, and try and unpack the question, which I ask myself a lot: what's gone wrong? Why have we made so little progress? Why is it all so hard? And I don't have answers. I can speculate a little bit. So I'm going to start off just by talking about computation, because I think ultimately computation is what drives robotics. It enables us to do the things today that we couldn't do a decade ago. And just over my own career, computation has changed a lot. When I was a university student, we seriously used slide rules. Calculators existed, but we weren't allowed to use them. We had to use slide rules. And so this mini computer down the bottom, that was a computer in my first job that I had. And this big thing here, like a washing machine on the end here, it was a 28 megabyte hard drive, right? So stuff has improved a lot between this decade and the decade we're in now. And this is a computer rig that I use for my own PhD research. I'm going to talk later about some things that happened in the 1970s. So if you consider the arc from 1970 to 2020, five decades, that's 25 Moore's law generations. And if you do the maths on Moore's law, it's a doubling in computation every 2 years. It's about an improvement of 33 million, right, in the computation that's available to us today to computation that was available to us in 1970. And that's a prodigious increase in computation. And I'd ask the question, what on earth have we done with that? Because we haven't seen a 33 million times improvement in the functionality or utility of robot systems. So that's computation. And then if you consider software, which is what we use to harness computation, which in turn drives robotics, then if you sort of consider consider programming languages, just classical programming languages, you could Pascal, probably the first modern, popular modern programming language from 1970, C, C++, and then Java. All of these things were done well before the year 2000. And then I'm going to just sort of drop in MATLAB, which is a programming language that's been very influential in my own career. And I started using MATLAB not long after MathWorks company was founded in 1984. So MATLAB first came out in 84. It developed the ability to handle objects and classes in the late 1990s. And my robot toolbox came out, first public release was in 1996. And I've evolved that ever since. And Patricia said some nice things before about the robot toolbox for MATLAB, and I'll touch on that again shortly. So that's another sort of stream of languages, which has got some connection to robotics through my own toolbox and through a lot of work that the MathWorks themselves are doing on tools for robotics. And we got Python, and the original Python actually is much older than people think. Python 1 came out in the very early 1990s, and we had Python 2 and Python 3, which came out 2008, I think, and is still going. So these boxes just indicate when something was released, not its duration. And then in terms of robot programming, most of you are probably not old enough to know of something like VAL, but it was an interpreted language that came in Unimation Robots. It came out in, I think, 1974. It was actually a remarkably capable language, and I'll touch on it again later. And then people have looked at other ways of how you express robot programming. And there's been work on embedding robot programming primitives into an existing language. And Richard Paul did some work on embedding robot programming facilities into a general purpose language like Pascal. And then later on, we've had ROS. And then I add ROS Noetic here, only because it was really ROS is very pervasive. It affects the way so many labs do robotics, the way so many people think about robotics. I would say for better or for worse. But for the longest time, ROS, for all its power and utility, really held people back by restricting them to either C++ or Python 2 programming. ROS Noetic was really the first one where you could combine Python 3 with the utility of ROS. And I think that came along rather too late. But anyway, it's out now, and that is a good thing. Someone just mentioned about JavaScript and in WebAssembly language, which is an amazing technology for letting us run software in a browser in a way that is completely machine independent. So a lot of ideas about virtual machines, but now we can run really complex apps inside a web browser. So where do we go next? What are things that I'm excited about from a robot software perspective? Because I've always been interested in the software for programming robots. And I think some interesting stuff is going to happen down here with JavaScript, WebAssembly language, and so on. And I think exciting things are still going to keep happening in the Python landscape. And I want to watch that. But there's a really interesting development. There was a keynote at the recent PyCon about PyScript, which is basically Python running in a browser, all implemented in WebAssembler. And this, to me, is enormously powerful, particularly for education and for research, maybe not so much for controlling real physical robots. But there's still lots of exciting stuff happening in the robot software space. And then I want to talk briefly about algorithms, because algorithms and theory is the other thing that drives robotics. There's no point having computation if you use that computation to implement algorithms and theory to allow robots to do the things that you want them to do. So back in the very early days, there was an algorithm called resolve rate motion control. It lets a robot manipulator move its end effector along a straight line. And we're going to come back to this in a moment. So it's the only reason that I mentioned this particular paper. But it's beautiful, it's elegant. And all the robot kinematic stuff was worked out in the 70s, and it appeared in these two very early textbooks. Some of you may have seen, maybe they are no longer in print, but they were kind of like the first textbooks, and they laid the scene for how we think about robot programming and robot algorithms and homogeneous transformation matrices and transform chains and all that stuff, all mapped out in the 70s and 80s. And then some people started to think about robot dynamics. Dynamics came well after the kinematics, and some more books came out that touched on those topics. And then people started to think about robot force control. And there's some great work happened in the 80s. Much of that was captured much later in the book by Siciliano and others. The yellow boxes here are books, by the way. And then there's another interesting thread. These two books, one by Richard Murray and one by Park and Lynch. And they are the people that introduced this whole notion of Lie groups and Lie algebras into the robotics community. It's been known in mathematics for 100 years, but now we start talking about the SE3 group and the SO3 group. All of this language was brought into robotics by Murray and then Park and Lynch. So they've thought about other ways to represent poses, which is really important in robotics. And then we had a bunch of people thinking about planning in the mid-2000s. And then we brought statistics in, the work of Sebastian Thrun and others. And then my book, which came out in 2011, just kind of snuffed everything that came before and tried to summarize it in a readable way. So it's got dynamics and the kinematics and the vision and the SLAM, a little bit of everything. And so now the books we have are really quite complete coverage of theory. But much of the theory, the point I want to make here is that much of important theory was mapped out a very, very long time ago. Yet it's still not readily accessible or widely used. And to me, this is a big frustration and what I want to talk a little bit more about. All right, so here are two pictures which are interesting to me. So this is a family of robots of different sizes from 1978, and here's a family of universal robots from 2020. And so with respect to algorithms and other sorts of capability, fundamental design of machines, have we really moved forward, or are we just going in circles? I really don't know, but I'd like to talk about that. back in 1978 with a Unimade robot, and I actually used one of these things. It had this programming language called VAL, which I mentioned before. It's pretty capable. And if I wanted the robot end effector to move in a straight line, I'd use a command like this. I just say move in a straight line, and then I could give a transform expression. So I could say move to a position defined by the tray. Relative to the tray, I want to move to a glass, and relative to the glass, I want to move to a grass pose. And it would solve the transform equation, and it would move in a straight line. If I wanted to do that today in ROS, it would be hundreds of lines of code, not at all intuitive. And I think that's a step backwards. I do not understand why the simplest things we want a robot manipulator arm to do is now become so hard. I think it's a really big barrier to anybody who wants to start. It's probably a really big barrier to people in industry who want to do a thing. So I talked before about, I gave this diagram before. So if you consider the business of how you make a robot end effector move in a straight line, the algorithm you need is the Whitney's resolve rate motion control. It's 5 decades old. That's 2 generations of humans. If you consider a generation of humans to be 25 to 30 years, which is what Wikipedia says it is, it's 10 PhD generations. So what is it after all of that time? It's harder to move the end effector of a robot in a straight line than it was in 1974. I just don't get that. The other thing I think that's a really important capability for arm robots is force control. And here are some examples from a video Osama Khatib put together a long time ago. And these are all results of robots doing force control from the 1970s and 80s. It is a really important capability for any robot that interacts with the physical world. Yet it really wasn't until 2018 that we have the Frank Remica Panda. It's probably the first commodity robot that's actually capable of implementing these algorithms from the 70s and 80s. Still not easy to access. You still need to write an awful lot of code to get access to that capability, but the robot can at least do that. So all that theory was from the 1980s, and so we're back about 3.5 decades. So we know the theory, but for various reasons, it doesn't get out into the world. It doesn't get out into practice. Though I'd argue it's really important that robots have these kinds of physical capabilities. So the question, why is it that we're going so slowly or backwards? And what really is the problem? Is it the intelligence bit? Are we sort of being distracted by trying to create a general artificial intelligence, and we've lost focus on everything else? Is it the machines are no good, the mechanism of the robot? Is it energy or sensors? Is it that there's no value proposition? There's no economic case to do these things with robots? Is it integration in software? Is that the problem? Or is it all of the above and more? Is that why it's such a wickedly hard problem and we are not making progress? I think perhaps if we understood what it is that's hard, what it is that's holding back, we could do some sort of divide and conquer thing and put groups of people to work on trying to break down these barriers so that we can all as a community move ahead much more effectively. So that's my interpretation of what's come in the past, and talk a little bit about what I'm up to at the moment, and then talk about some future problems. So things that I'm working on right now are books. Books are eating my life at the moment. So the original version of my book, which many of you are perhaps familiar with, came out in 2011. And it was a second edition, came in 2017, and then there's a split version. So instead of one very thick book, there's 2 moderately thick books, which came out this year. And next year, I'm hoping that there will be 2 third editions of the book. So the first one up here is an all MATLAB version of the book. So it is a closed source version of the book. The previous books, you needed to buy MATLAB, and then you could use my open source toolbox. This edition of the book is all closed source. So you need to buy MATLAB, and you need to buy all of these various MathWorks toolboxes. But for people in industry or people in education who have access to all of those toolboxes, it's it's a very viable and powerful solution to the problem. So that's this third edition. The other third edition is everything has been redone in Python, and it is completely open. Python is free, and all of the toolboxes that you need to run all the examples in the book are also free. So both of these books should come out early in 2023. So this has been a huge project. This one in particular, because all of the toolboxes that I've written over 2 or 3 decades in MATLAB, all ported to Python, and then the book rewritten to change the narrative to suit that. And then I've also been working on all the Python tools. So there is now a robotics toolbox for Python. It's been out for almost 2 years now. It's now at release 1.0. It's pretty stable, and a lot of people are using it for teaching and tinkering, which is great. So it's got arm robots, it's got mobile robots, all the differential kinematics, forward and inverse kinematics, dynamics, all of that stuff, collision detection, visualization, that's all in that toolbox. There is a machine vision toolbox for Python. It essentially wraps OpenCV and Open3D, but it provides a much nicer interface to those libraries and does all of the things that the old MATLAB machine vision toolbox would do. There's a separate toolbox that's been factored out, which does all the stuff with homogeneous transformation, matrices, rotation matrices, twists, quaternions, all that stuff. There's a graph class, there's a browser-based graphical simulator, and there's a block diagram modeling package. So it's like a Simulink Lite, which also supports some examples in the book. So it's been a fun time writing lots and lots of code, which is what I like to do. But what I really want to get to is to have an abstraction in software for robots that lets me express something like this, and as elegantly as this. I don't want to have to write pages and pages of ROS. I want to say, robot, move to this pose with Cartesian interpolated motion, that's straight line motion, until you see a force that's greater than 5 newtons in the Z direction, or until you've traveled more than 1/10 of a meter. And it shouldn't be any more complex than that. It should be essentially one single expression that allows the robot to do something sophisticated. I haven't implemented this, but this is what I think about. This is, I think, what we need to make it very easy and convenient and safe to get robots to do more complex tasks. All right, future. What are things that I think we should be thinking about? And my scope here is fairly limited. I'm still very interested in robot manipulators, more so than mobile robots, and I'm still very, very interested in vision. So that bias is going to influence the things that I list here. Using vision to control a robot manipulator is still rare. So the video on the left is from some work by Al Rizzi and Martin Buehler from '95, and they would have hand-coded a completely bespoke system to do this. The example on the right is done by one of my PhD students. He still had to write more lines of code than I think he should have to just do this very simple snatching maneuver as a robot end effector moves towards an object. So we need to find out what are the things that get in the way of people doing this. What are the pain points, and develop software tools that take them away. I think in terms of computer vision, I think we need to make much better use of context. So in a scene, if you know that you're in a living room, then there are things you would not expect to see, including a gorilla or a motor car or an aeroplane. And so I think instead of looking at a scene and trying to classify all the objects within it, if we knew the sort of scene that we are in, then we could use that to make actually the object classification task a whole lot easier, because there's a much smaller set of objects that we would need to be thinking about. The challenge is that in order to determine the context, we do need to use vision. So we need to use vision to determine the context that we're in, and then use that context to help us understand the scene better. So in some ways, it's a wicked problem because we need to see to establish context in order to see. But I think it's an interesting problem, and I don't know why we don't make better use of context. It's clear, and we've known for a long time, that moving and seeing are deeply connected. So this pigeon is using motion of its head to enable it to see better. in particular to give it some 3D perspective that it otherwise doesn't get. And we've known about this coupling between seeing and moving for a long time. I use my sight to help me walk and to balance, but I also use motion. I move my head if I want to see, learn something more about the scene, to disambiguate something, I use motion. And the concept of active vision goes right back to the early 80s. And it's something we talk about a lot. Everyone knows about active vision. We still don't do it. And it seems so obvious and so useful. And I don't know why it is that we don't do active vision. I think we should also pay attention. And so our visual system uses our eyes to answer questions. So when we look at a scene, we don't make a visual inventory of the scene. We move our eyes over the scene in a way to answer the question that we're asked. And studies have been done many decades ago, and the picture on the left shows this. If you ask a human observer that question, what are the material circumstances of the family? And you watch where their eyes move using a gaze tracker, you see the trajectory that their eyes follow. If you ask them a different question, their eyes will follow a different trajectory over the scene. And you can see in this case, the person's eyes are checking out the paintings on the wall, looking for jewelry, and sort of ornamentation, evidence of wealth, which is fascinating. And if I'm considering the picture on the right, if I'm a mobile robot and I want to move into the next room through that doorway, so all this stuff in the scene is completely irrelevant to me. I don't care about it. So why build a visual inventory of the whole world, classify all the objects and localize them, and then throw them all away? It just is a waste of effort. So I think we need to pay attention to the things that are specific to the task at hand and not to anything else. And then part of all these things, I think, lead to human ability to do that visual processing using only 6 watts of power, when most vision algorithms we run today run in on a GPU or a rack full of GPUs and consume kilowatts. So I think this is another aspiration for us as vision and robotics people, is how do we do all this using less energy? And in biology, we've developed lots of tricks: attention, context, focus, which we don't use in robotics. And they may be key if we want to do this stuff using low power. Another thought, and this is a sort of paper that this is a paper we wrote a couple of years ago now, really looking at the very different research methodology between a computer vision community and the robotics community. Computer vision people have a very different way of working. And in robotics, we talk about doing experiments, and really what we do, what we call experiments in robotics, are in no way experiments. Nobody in robotics is testing an hypothesis. I think perhaps we should. The vision people have made enormous progress. If I look someone with a foot in each camp, to me, the computer vision people have moved much, much faster than robotics people. And I think it's down to their methodologies: rapid publication, competitions, benchmarks, clearly defined metrics, clearly common data sets. And yeah, they've made enormous progress. So I speculate about some of those, and you can find that paper on arXiv. So that's really what I wanted to say, to challenge you to perhaps to think a little bit about the question: are we making progress? If we're not making progress, why are we not making progress? So thank you for listening and indulging me. I'm very happy to have a conversation, take some questions.
Great. Thanks a lot for your talk, Peter. It was really, really interesting. I'm now asking everyone in the audience, if you have any question, please raise your hand or write in chat. We also created a Slack channel. So if you prefer to use Slack, you can also write on Slack or ask yourself if you want. That just that. I give you. Do you have any question? Yes, please.
Hello, Professor. It was great to hear you speak today. And I wanted to ask about your comments you made, like how you used, you could just use the VAL program in 1970s and just like abstractly say what the robot should do, while
Mhm.
doing the same thing in ROS takes so much more effort today.
Yeah.
So how do you think the effect of ROS being an open source tool and FAL and the Unimate being an organization that made a product which was probably super expensive at that point of time, that matter in this? Because like when you're developing an open source tool, I think a lot of us would, you know, take 2 steps and think more if we should already, if there's something that's already been done, it doesn't attract to, you know, kind of reinvent the wheel or like implement something. Because but if you're a company who's selling a product, you would probably have to go the extra mile and make things easier for your user.
Look, it's a really good point that you make, right? One is Val certainly was a proprietary solution, so you had to pay a lot of money to the company to buy, you know, the robot hardware and the control computer and the language and all of that. So, and I think we should be moving away from proprietary solution. I'm a big open source fan. Don't get me wrong about that. It was really just the point I'm trying to make is about those proprietary tools. They're very old, but they had a certain utility or usefulness. And just because it's open source software, it doesn't need to be complex. I think my frustration is that the open source software we're creating is just too complex, and that creates a barrier to entry for somebody who wants to get into robotics. So to me, a better solution would be something that had perhaps the utility of the VAL software, but it was open source, and maybe it sat on top of ROS. So maybe it's just a simple, powerful programming language, an interpreter, if you like, which under the hood, it talks to ROS, hides ROS. I mean, ROS is still great because it's got drivers for so many different sorts of robots, but perhaps, you know, kinematics, trajectory planning, all of that stuff is done under the hood by this new programming environment, or you just embed it in the Python language. So that little example that I gave about how I'd like to express a robot motion, that's actually done in Python syntax. And I'm pretty sure you could do all of that just using Python's existing class mechanisms. So, yes, I think we need to keep ROS. And the big thing that ROS did that was really valuable is that it stopped every lab in the world from developing its own middleware. And so I was working at a not at a university, at a government lab in the 90s and early 2000s, and we spent a lot of effort developing our own ROS. So our own robot middleware, and it used shared memory and multiple processors, and they could communicate and do stuff, all the things that ROS did. But our lab, we built our own to do that. And most other robotics labs did that as well. I think across NASA, they probably had half a dozen robot middleware packages. So the thing that ROS did was stopped all the labs wasting time on their own middleware. They produced a workable standard middleware that everybody could use. We might complain about some of its features or design aspects, but it did save us all from wasting a lot of time. So it was really good for that. But I think we just need to put a lid over it and provide a more effective interface to users, or to a class of users. No interface is going to be useful to all users, but I think we could do better.
Thank you. That answers my question.
So Dan, if you want to ask your question.
Sure. So you made this comparison between work in computer vision and robotics, and you said computer vision seems to go faster because they have, you know, more rigorous testing and shared data sets and everything. What you didn't say, and what I'm curious about, is the fact that robots have to operate in the real world.
They do.
Vision, I can just rerun data. I cannot do that with a robot. So how does that impact the relative speeds of these fields?
It's a really good point. The analog for robotics the analog to a computer vision data set for a roboticist has to be a simulation, right? It has to be a physics-based simulation, because however, the pose of the robot and all of its sensors is a function of all of the previous decisions and sensory input that the robot has received. So in order to get the appropriate sensory input, yeah, you need to have a proper physics-based simulator. And maybe a decade ago, that was super hard to do, but simulation technology has improved. It has improved a lot. There will always be a gap, right? There'll be perhaps robot results you get in simulation won't exactly match what you get in the real world. But just as the vision people find that there's a discrepancy between the precision recall results they get from data sets versus what you get in the real world. But I think that's a way that we can make much greater progress, because the experiments will be less onerous to do. We can run experiments faster than real time, but also it means that you can compare two different algorithms in exactly the same simulated physical environment on the same simulated physical robot. And that's something that we really can't do at the moment. So to me, it's the solution to match what the vision people do. We need to adopt simulation.
So just a quick follow on there. What about robots that interact with humans? So now, do we need a human simulator in our physics simulator?
All right. So I guess it depends what it is that you are trying to, measure. I mean, if you were just looking in general at the sorts of robot behaviors characteristics that humans find easy to work with, you're probably going to have to be doing sorts of trials that psychologists would run with large populations of diverse people and build statistics. But if you wanted to simulate in a repeatable way how a robot responds to a human, yes, I don't know how you would do that actually, Dan, because if you've got a human doing gestures or whatever with a robot, that's never going to be repeatable. The human is not going to be accurate enough to allow you to do repeatable experiments. So either you do trials over large numbers of people, or perhaps you create some avatar and present it to the robot.
I don't have an answer either. So
yeah,
thank you.
Bara has also a question. Bara, do you want
Sure.
to?
Hey, Bara.
Maybe there's their hands up. Okay. Maybe when he will be back. Okay, there is another question from Hamid and another from Marcus. So Hamid, can you?
Do you have my voice?
Yes.
Yes.
Thank you, Peter. It was a really fascinating and interesting talk. I would like to mention two maybe comments or two topics to further.
Sure.
The first thing is robotics and education. If I compare robotics in education to other fields like what you mentioned, vision or something, I find robotic much more interesting because it has a human body, it has a mechanical body, it has the software, it has everything all embedded for the student, for newcomers in the robotic world to see what is going. And I think that what we are doing and what we are using robotics in education, it is quite well compared or well evolved during the years. But when we go through the research, on the other point, I'm quite in line with you, what I think, and also my experience. We used to do a lot of things in the research, which might be not as good or as measurable or as desired from 50 years ago. For example, we are doing right now in our group a lot of robotic application in medical and surgical, other kind of applications. But when we are in a robotic group, we are in the robotic community, everything is fine and everything is glorious. But when we go in an operating room, in a real, scenario in the hospital, it is very difficult even to bring the robotic into the surgical room. We are happy to do the research because we are keen to do that. We would like to do the impedance control or something on a real soft tissue, but what the real application requires, or what the real application will actually oblige us, is a bit farther. It is we are maybe a bit farther from the horizon that it is really needed. And I guess comparing that to vision, it is quite different, because in vision you see that there is a lot of vows coming, and a lot of application, a lot of big data coming, and so there are so many communities working on that. The final, I would like to have your comments, of course, but my thought was, what I get from your very interesting talk was just to sit back and see, are we evolving in the right way? Are we working in the right path? Or just we are, curious enough to fulfill our curiosity rather than doing a real application in robotics?
I think the point that I was trying to get across is, there are things that we think we know how to do, and we have theory. Impedance control, for example, which is something that you mentioned as well. And we've known this for a very long period of time, but when any of us actually comes to implement it, we find ourselves in a world of pain. So I think the theory is not wrong, but we do struggle to implement it, and then we just don't have enough good reference solutions that we can draw on. So the capability isn't built into products, and maybe we don't have good enough or robust enough open source solutions to these things. But there are things as roboticists we just shy away from, like using vision in the loop. If we want to grab something, we know that we could make an object detector that'll tell us where the object is. That's easy. But when it actually comes to integrating that into the robot controller, suddenly it becomes really, really hard. And a student or someone will spend weeks doing this. The question is just why? Is it the tools are wrong? I don't think the theory is wrong, and I think we have enough theory, but there's something deeply wrong with the tools that we use, that I think they get in our way rather than help us. And that's the thing that I'd like more people to think about. Actually think about the pain points and do work to address the pain points. Perhaps in our community, we don't respect that kind of work enough, and people will say, "Oh, that's just engineering. That's not worthy of an ICRA paper." I think there is probably some of that as well. But I think unless we address these, we are just gonna stall as a field and stop moving ahead.
Or maybe we are doing something more sophisticated than it really needs to be. This could be also a reason.
It could be that that there are things that maybe you could do more simply than use an impedance controller. But impedance control, that the concept is lovely. It lets you do all sorts of great things with a robot, the sorts of things that humans do every day and effortlessly. Why can't we have that? What stops us having that?
Thank you very much.
Thanks, Hamid.
Please, Marcus, go ahead.
Okay, thank you, Peter, for your interesting talk on the complexity of software development in robotics. Also for your Python toolbox, which I think is really great because it lowers the barrier.
Thank you. Patricia, I think I've lost Marcus.
Yes, or did I think?
When, sorry?
Uh,
So you were visiting Tamim's lab 3 years ago.
Mhm.
And you noticed the humanoid robot ARMA 6, which was introduced like 4 years ago, which has even more degrees of freedom. It can move around. And we also have something, we already have something like this robot.move in Python. Also like robot.gaze.look at in Python. And I think so Tamim's lab is really strong in integrating stuff on the getting things running on the robot. And I think it's also like the team effort to work on such things. It's not only the complexity in software, but it's also the human complexity that we need to work together on that. I also noted that all the everyday tasks, they're really complex. And I think they're like, maybe they're too complex to model them with like robot.move and robot.look@, with these primitives. And currently I'm visiting Dieter's lab, and I think end-to-end learning might be even the way to go instead of programming things. Can you comment on that?
It's a really good point that maybe this whole business of programming robots is going to just end up on the side of the road, you know, on our journey forward to robots that are truly useful. So that is very possible that we may bypass the need for that. I'm not sure we are there yet. I don't know what's going on in Dieter's lab with how effective the end-to-end learning is. But if we could, I guess one future nirvana for robots that people talk about a lot is just to do things by demonstration. You show the robot once, or you tell the robot in a sufficiently descriptive way that it can do the task without any programming at all. That is probably where we would want to get to. But I think we're still going to need this crutch of robot programming for a class of applications, and you know, for, I would guess, at least a decade into the future. So if Tamim is doing that good stuff in his lab, then that's fabulous. Maybe there are people in other labs doing the same thing. We might start to do some similar sort of higher level programming abstractions in our lab. And then we get back to the problem we have with Ross, right? There's a need, everyone starts to satisfy that need in their own way, in their own lab. Again, that's an inefficiency. So somebody should factor that out and make it an open source project. I'm not sure if that's a full answer to your question, Marcus, but it is a good one. And I have to say, learning is probably something that's never uppermost in my mind, and I'm going to put that down to being a generational thing. I guess I grew up with the paradigm of programming and control as sort of classically understood, and learning, which is what all my PhD students are thinking about and doing. It's still not the first solution that ever pops into my head.
Good, thank you.
Bara is back.
Yes, sorry, I had a technical issue before. First, let me thank you for the talk and for also the online courses. I'm one of the people who enjoyed attending those and watching those.
Fantastic, thank you.
One of the things you mentioned about why do we care about, or why the robot cares about a lot of details, though it needs maybe just to move in the corridor or so. Do you think because we humans don't think about a high resolution, like I don't, when I move, I don't think about how many millimeter my hand is, or I am away from the wall. comparing when we use camera or LiDAR, we get that information, and that's the reason we have a lot of information, and we need a lot of processing power in order to analyze this information, comparing with a human that just basically walk and think about, oh, I just don't want to hit the wall, and I just, like, even if it's clumsy a little bit, we don't care, we do the job.
It's a good point, and I teach all my undergraduate students, in robotics. I teach them about coordinate frames and how coordinate frames are really useful. But coordinate frames gets us into a way of thinking about problems that's all about metric information. Where is anything with respect to anything else? And we humans don't have that. If I'm walking down the corridor, I don't know what the global reference frame is. I know I'm in a corridor and I want to stay away from the walls and other people. And so I think we do a lot of stuff that we solve a lot of tasks using relative positioning. And vision is a wonderful relative positioning sensor. It's actually not a very good sensor for metric information, but it's really good for relative information. And perhaps because we have evolved with non-metric sensors, we are able to do everything using relative positioning very, very effectively, because humans are still way more effective than robots are. So I think that there is a lot of utility. A lot of utility in expressing robot tasks in relative ways. I think would be more powerful and more robust than trying to do everything with frames of reference.
But the thing is, you don't expect that from a robot. You expect a robot to be precise, accurate, and nailing to the point and repetitive and so on. And you cannot do that unless you have that high resolution, high data, and high information in order to analyze. In a human, even if you knock off a cup, you know you are not going to destroy it or throw it or damage anything, but a robot will. So that's the reason you need that much information, which will give you a headache analyzing it and processing it.
But this is the problem with precision. If you got high resolution point clouds from LiDARs or stereo, then you've got to do a lot of processing on all of that data to, I guess, to reduce it to an amount of data that you can use for control purposes. I think the robots that we have today, their heritage is from industrial applications, manufacturing and so on, where precision has been always very important. And so I think we have gone down the wrong road and try to think of everything in terms of positioning, and precision. So if I want to do precision positioning, then I have to have precision sensing to tell me where it is that I want to go. So if I want to pick up that object, I need a sensor that can tell me its pose with respect to a coordinate frame, and then I've got to accurately move my end effector to that particular pose. So I've got to solve two hard problems. I've got to figure the pose of this guy, and then I've got to do accurate control of this guy, right? And that's nuts. Why solve two hard problems if you don't have to? So I would argue, simply superficially with a lot of hand waving, all I need to do is make this thing go to that thing. So all I need to just control it so that the distance between them is zero. And visual servoing is one example of doing that. We do control by making two things coincident in the image. Now, that's easy to say in a hand waving way. I think you can solve a lot of tasks that way, but not all tasks. But if there are some tasks we can solve that way, then perhaps we should.
Thank you.
Great. Let's thank Peter for the amazing talk and discussion today. Thank you so much for being here.
Thanks, everyone. Thanks for the questions. That's great.
Very interesting. And I am going to just close the session by thanking all of the sponsors that enabled to do this: Animata, Semu, and Paul Robotics. And we are closed for a vacation break, a summer break. So happy holidays and enjoy the sun or the winter break, whatever you are in the world. Thank you so much. Bye-bye.